This exercise is a proof exercise for the convergence of the secant method when it is used under certain conditions to approximate the roots of the equation f of x equals 0. The function f is given to be continuous and with positive first and second derivatives. Suppose that a sub 1 is greater than a sub 2 is greater than r, where x equals r is the unique solution to the equation f of x equals 0. Starting with a sub 1 and a sub 2, let the sequence a sub n be the sequence of estimates generated by the secant method for x equals r. For this lecture, we proved that the sequence a sub n converges to x equals r. We subdivide the proof into two parts. We first proved that the sequence converges, and so for the first part, we show that the sequence a sub n is a bounded monotone sequence. In the second part, we showed that the limit of the sequence a sub n is indeed equal to r. Before we write out the details of the proof, let us review the secant method. Given the two initial estimates a sub 1 and a sub 2 for x equals r, we find what is called the secant line determined by the corresponding points on the graph of f. Since f prime is greater than 0, this secant line should be transversal to the x-axis and should have an x-intercept a sub 3, which is now the next estimate for x equals r. Then we use the points at a sub 2 and a sub 3 to find the next secant line. The x-intercept a sub 4 of this new secant line is the next estimate for x equals r. In general, with a sub n plus 1 being the x-intercept of the secant line determined by the points at a sub n and a sub n minus 1, a sub n plus 1 equals a sub n minus f of a sub n times the quantity a sub n minus a sub n minus 1 divided by the quantity f of a sub n minus f of a sub n minus 1. We begin with the first part of the proof where we show that the sequence a sub n is bounded and monotonic. We proved by mathematical induction that the sequence a sub n is strictly decreasing with all the a sub n's being greater than r. For the first part of the induction, we are given that a sub 1 is greater than a sub 2 is greater than r. For the second part, we assume that a sub n minus 1 is greater than a sub n is greater than r for n equals 2 all the way up to some integer k where k is greater than or equal to 2. Hence, a sub k minus 1 is greater than a sub k is greater than r. We now show that a sub k is greater than a sub k plus 1 is greater than r. According to the secant method recursion, a sub k plus 1 is given by this formula. F prime is greater than 0 so that f is strictly increasing. Since f of r equals 0 and a sub k is greater than r, f of a sub k has to be positive. A sub k minus 1 is greater than a sub k so that a sub k minus a sub k minus 1 is less than 0. Likewise, f of a sub k minus f of a sub k minus 1 is less than 0 since f is strictly increasing. Therefore, the right side of this equation is less than a sub k, so that a sub k plus 1 is less than a sub k. To complete the induction proof, we must show that a sub k plus 1 is greater than r. We define the function g where g of x equals f of a sub k plus the quantity f of a sub k minus f of a sub k minus 1 divided by the quantity a sub k minus a sub k minus 1 times the quantity x minus a sub k. G is simply the secant line through the points at a sub k and a sub k minus 1. Then we define the function h where h of x equals f of x minus g of x. And so h prime of x equals f prime of x minus g prime of x. G prime of x is just the slope of the secant line so that h prime of x equals this quantity. It is now time for the mean value theorem. Since f is differentiable, there should be a value c between a sub k and a sub k minus 1 such that f prime of c equals the slope of the secant line. And so h prime of x is also equal to f prime of x minus f prime of c. Now f double prime is greater than 0, so that f prime is strictly increasing. Therefore f prime of x is less than f prime of c for values of x that are less than c, so that h prime of x is less than 0 whenever x is less than c. Hence, h is strictly decreasing for x less than c, including at a sub k and a sub k plus 1. Since a sub k plus 1 is less than a sub k, h of a sub k plus 1 must be greater than h of a sub k because h is decreasing. Now h of a sub k equals 0 since f and g intersect at x equals a sub k. And so h of a sub k plus 1 is greater than 0, which also means that f of a sub k plus 1 minus g of a sub k plus 1 is greater than 0. Because a sub k plus 1 is the x-intercept of the secant line, g of a sub k plus 1 equals 0, and therefore f of a sub k plus 1 is greater than 0. But if f of a sub k plus 1 is greater than 0, and if f of r equals 0, a sub k plus 1 must be greater than r if f is strictly increasing. This completes the induction part. Therefore, the sequence a sub n is a monotone sequence bounded above by its first and biggest term a sub 1 and bounded below by x equals r. By the bounded monotone convergence theorem, we now know that the sequence a sub n converges. Whether or not its limit is r is the subject of the second part of this proof exercise. We use proof by contradiction to show that the limit of a sub n is r. Let the limit of a sub n be a value b. B cannot be less than r, because if b is less than r minus b will be positive, and we could use epsilon to be equal to r minus b. But we have just shown that a sub n is greater than r for all values of n, and so a sub n minus b is greater than r minus b or epsilon, and so b cannot be the limit of the sequence a sub n, and so b is greater than or equal to r. One can use a similar strategy to show that a sub n is greater than or equal to b. We leave the details as an exercise for the viewer. We showed that b equals r by contradiction, and so we assume that b is greater than r. We choose a new epsilon, and we choose it carefully. We set epsilon equal to 0.5 times f of b divided by f prime of a sub 1. If b is greater than r, and if f is strictly increasing, then f of b must be positive. F prime is given to be greater than 0, so that we do have a valid choice for epsilon. Since a sub n converges to b, we can choose uppercase n so that the absolute value of a sub n minus b is less than epsilon whenever lowercase n is greater than uppercase n. Therefore, a sub n is bracketed by b minus epsilon to the left and by b plus epsilon to the right. And it is mean value theorem time once again. There is a valued c sub n between a sub n plus 1 and a sub n such that f prime of c sub n equals the secant slope between a sub n plus 1 and a sub n. Since f prime is strictly increasing and c sub n is less than a sub 1, f prime of c sub n is less than f prime of a sub 1. By the secant method recursion, a sub n plus 2 equals a sub n plus 1 minus f of a sub n plus 1 times the quantity a sub n plus 1 minus a sub n divided by the quantity f of a sub n plus 1 minus f of a sub n. Let's have a little mano a mano on this equation. Since n plus 1 is bigger than lowercase n is bigger than uppercase n, a sub n plus 1 is less than b plus epsilon. This fraction is actually 1 divided by f prime of c sub n. and epsilon is 0.5 times f of b divided by f prime of a sub 1. Therefore, a sub n plus 2 is less than v plus 0.5 f of b divided by f prime of a sub 1 minus f of a sub n plus 1 divided by f prime of c sub n. We carry out another mano a mano, this time with this fraction. Since f is strictly increasing and the limit b is a lower bound for all of the a sub n's, f of a sub n plus 1 is greater than or equal to f of b. And we already know that f prime of c sub n is less than f prime of a sub 1. So this fraction has to be greater than f of b divided by f prime of a sub 1. But the minus sign in front changes the direction of the inequality, and we obtain a quantity that is at least as big as a sub n plus 2. This part is negative, and therefore a sub n plus 2 is less than b. This is a contradiction because the limit b of the decreasing sequence a sub n is also a lower bound for the sequence. And so our assumption that b is greater than r has to be false, so that b must be equal to r, and so the limit of a sub n is r.